last speaker of this session is Takao Suyama from KEK, and the title is Dynamics of a Revolving D-Branes at short distance. Thank you.
Okay, so I'd like to thank the organizer for the invitation. Okay, so this talk is closely related to the previous talk by Susan, and mainly I'll cover some technical parts. And some parts will be overlapped, but maybe it's very good to repeat it. And this work is based on the Susan and Ota-san, he's a student of Susan, and Kitazawa-san in the Tokyo Metropolitan University. Okay, so actually one of the mission of our project is to calculate the effective potential between the revolving D-Branes, moving like this. Actually, when I got this mission from Iso-san, honestly speaking, I thought that this is impossible. It's too difficult. But also, it's impossible to say so. So I just say, okay, let's do that, and try to think about what can be really done. And first thing we could do is to do some perturbative calculation for the effective potential, and we got this potential. Actually, I like this formula. This is rather non-trivial, and still it's rather compact expression. But actually, people say that it's too complicated. They're complaining. And actually, this is not so useful because even though we want to extract some information about, for example, the possibility of the bound state or something, but it's too complicated to say something from this. So we have to do something else. And then recently we found some method called partial module transformation, which was briefly explained by Iso-san in the previous talk. And this turned out to be give a very good approximation for example, one loop partial function. Actually, basically the same idea was already used in this paper in some qualitative argument. And in our work, actually, we use same technique in the qualitative purpose. And using this, we found that this is kind of the very efficient method for calculating some offshore quantity, like effective potential. And it's a revolving D-Branes are not onshore configuration, so the worldsheet calculation has some problems. But using this kind of the method, actually we can calculate such kind of the potential. Okay. Let me explain what kind of the calculation we have done by using some simple method which can be calculated exactly. And let's think these three D-Brane system, which are not revolving but somehow rotated relatively. Okay, static configuration, but some D-Branes at angle. Okay. And if you look at Polchinski's textbook, then you can find a formula like this. Okay, this is very short expression, but still rather complicated function. So let's see what kind of the function it is. So, well, of course, we know something about this potential. For example, this R is the distance between these two D-Branes, and the distance is very large, then this potential approaches to the usual Newton potential. And mainly we are interested in the potential where this distance is very small. And one might think that in that case you can just take into account the contribution from the massless open strings. But actually, it is not correct. And if this R is very small, then all the massive modes are contributing equally. You may say that there is some kind of the suppression factor for the higher massive terms, but because the integration is from 0 to infinity, so this is no more small in the for the small t. Okay. And also, we want to find some approximate expression which can be applied to all the range of the distance at once. So what can be done? So let's start from this one. This is the starting question. And then, okay, divide the integration region into 2. Okay. And then do the modular transformation only for this second one. Okay. Usually this is from 0 to 1, and this becomes 1 to infinity. Up to here, this is just the exact computation. And then expand the theta functions and obtain this one, just retaining the leading terms for each terms. Okay? So then, well, expression becomes much more manageable. But of course, this is the expression because we discarded all the higher order terms in the expansion.
What's the expansion parameter?
Well, this is just a Q expansion of the theta function. So, but actually, there is surprising that this gives a very good approximation. So this is the plot. Well, you might notice that there are actually two curves in this plot. One is the red curve, and the other is the blue dash curve. Actually, I don't remember which is which, but the one is the exact. One is for the exact expression, and the other is the approximate one. Okay. If your eyes are very young, then you can maybe distinguish these two. But of course, I would say that this is a very good approximation. And I want to emphasize that the approximation is good for all the range of the R, from small r to large R. Very nice. And this is not the just we are fortunate, but there is a reason. Okay, so I said that the expression is like this, so the integration is from 1 to infinity for both expressions. And then, as I said, that the higher massive terms are suppressed by this one, this factor. And because this t is larger than 1, so this is always less than this factor. And this innocent looking factor is actually a very, very small number. This is 0.0018 something. So because of this cutoff for this integration, these higher order terms are highly suppressed. And you may be worried that, in the string theory, the degeneracy of each mode are very large. But the growth of the degeneracy is only exponential to something times the square root of n. And the suppression factor is actually e to the n minus 2 pi n. So the suppression always wins, finally. And actually, you can analytically estimate the error in a simple situation. For example, parallel D-Branes in the bottom string. then error turns out to be less than 3%. And if you also include the next order terms, then the error is much smaller. Well, actually, I should say that there is another implicit assumption. So this approximation is good if the mass spectrum has a property such that each gap is of order of the swing scale. So if the rotation becomes large, then the swing spectrum becomes deformed so that some mass state becomes very light. Okay. Then actually this approximation will break down. So only when this angle is very small, this is good approximation. Okay, so basically this is the calculation we have done, and schematically we obtain this kind of expression. So the potential is given by these two terms. One is contribution from the light open swing states, and the other is from the massless closed swing states. And the point is that the integration is from 1 to infinity, not 0 to infinity. And because of this cutoff, even though we add open swing contribution and closed swing contribution, but this is no double counting. Okay. And this can be said in this way. So this can be given by the bounded calculation in the Suyama mills, and this can be obtained from the tree calculation in supergravity. And from this expression, we notice that this kind of calculation can be done only when we can quantize the open stretch between D-Branes. But for this calculation, we can do. This is just a usual field theory calculation. Okay, and these are official formulations, so official calculation in string theory. I also want to emphasize that this calculation can give good approximation numerically for the full stringy computation. Okay, so because of time, I'll just briefly explain the cases for the revolving case. What we have to do is to do some one-loop computation in the Suyama mills around this background field configuration. And for supergravity, the coupling vertex between the closed swing and D-Branes are obtained from the DBI action. And the emitting coordinates for the revolving D-Branes are given by this expression. And well, this is the expanded version of the Suyama result. Well, okay, one thing I want to say is that actually this expression decays exponentially when R is very large. Then that means that this will not contribute to the Newton potential. So this is another indication that we are not doing double counting. And the supergravity result is like this. And as a check, we can consider the large R behavior, for example, then this is like this. So if you are familiar with the old calculation in the D-Branes scattering, then this is quite similar to this potential, proportional to the V to the fourth power. And actually, recently, one of one student, Ota-san, actually found that this kind of behavior is quite general. Not for this revolving case, but the more general trajectories, this starts from the V to the fourth power. So this kind of behavior seems to be very general. And then, these this contribution will obtain this kind of potential, and physical implication of this potential is already explained by Iso-san, so I'll skip. Okay, so finally, I'll just briefly mention about the bound state we are considering. We are thinking about these three branes, but the bound state of the zero brane has been already studied for a long time. Well, maybe what you know very well is the so-called marginal bound states. Building B, building here, and you must know everything. And this one is the BPS bound state. And this is very important in the context of the BFSS. But actually, we are considering some rotating one, and supersymmetry is completely broken. So our would-be bound state is not like this one. And it is more close to the other one, already somehow studied by these people. And actually they claim that for these little branes, there are non-BPS bound states when angular momentum is non-zero. And we are expecting that our method can be some more argument about this kind of bound states. Okay, so let me summarize. So we somehow propose kind of the method to compute one loop effect potential in an approximate way, and this turned out to give some very good approximation, and this allows us to compute the effective potential for the revolving D-Branes. And well, there are several possible future work, and I hope that this kind of method will give us some very handy machinery to compute some official quantities in string theory. Okay, thank you for your attention.
Any questions or comments?
So in large radius, really is repulsive, not attractive at all. Because when you have velocity, there's a centrifugal force, and then you have v to the fourth over some r to the power. That's not that one of r scale repulsive forces.
Okay,
so it's not really attractive.
All right. So as Isun said, that
yeah.
this is not including the centrifugal potential.
Right. So
right.
it's completely.
So that's one.
There's no bound
confusing. But anyway, this is just the potential.
If the bound state is formed in the early universe, and this is explained, then there may be revolving with some angle, so you can combine it.
Well, it depends on the how powerful his student is.
Or how strong this host is.
Well,
how the bond will work?
well, I'm not sure.
But the basic data will be changed.
Of course, there are more parameters, but I think that the calculation will be not so much different.
If there's no further question, let's thank the speaker again. So we have a 20 minutes break. We come back after the last session. 5 minutes. Acceleration.
这个现象一个人。对，我就是。